Hello all. We're on section 8.3 now, and we're going to be talking about ATP and talking about energy coupling. So I'm going to start with energy coupling, and the idea of energy coupling is if you look inside of a cell and you want to do an endergonic reaction, a reaction that requires energy. For instance, take one molecule and another molecule, and if I would like to connect them with a bond, so this would be a condensation reaction producing water. That would be an endergonic reaction. It would have a positive delta G, and it's going to need some energy from somewhere, so we need an energy supply. So E for energy, and we're going to draw that as the arrow in there during the reaction. And the idea with energy coupling is in a cell, if we need energy, the best way to come up with energy for an endergonic reaction is to have an exergonic reaction to provide the energy. So we may do something like this. We've got these molecules down here that need to be combined. So in order to combine those molecules, we'll get energy by taking some other reaction. Maybe we have these two molecules that are already combined, and we don't need them to be combined, so we can do a hydrolysis reaction and separate the two molecules into their separate squares. And that would be exergonic. Again, that would have a negative delta G. Some of the ideas there from the last video is I'm separating these molecules. There would be energy stored right there in that bond, and that energy is going to be released when we break that bond. So breaking that bond is going to release energy, so we're going to curl an arrow down here and say we're going to have energy released from this reaction, the top reaction, and use that energy to feed the endergonic reaction, the one that needs energy on the bottom. So that's the idea of energy coupling. Happens a ton inside of cells. Anytime that they need energy for something, they're going to borrow it from another exergonic reaction. So that leads us to a very important molecule. I'm just going to pull this picture up here, called ATP, adenosine triphosphate. And ATP ends up being the molecule that is used in this top exergonic reaction. So I just drew these two squares together. The ATP ends up being the molecule that we oftentimes use as our source of energy. And so the way it works here, ATP is made of an adenine group. That's this up here. It's a nitrogen base. An adenine group, a ribose, which is a pentose sugar. We can call the two of these together adenosine. Okay, and then it's going to have three phosphates, and I'm noticing now that there's not a P in the middle of each of these, so there should be a P there, and a P there. So the triphosphate means three phosphates. Phosphates end up being negatively charged. You can see all of these have a negative here, a negative, a negative, a negative. And so if I'm going to have a bond that holds all these negatives together, it actually is going to require a handful of energy there. And so there ends up being energy stored in trying to hold these phosphates together. And so specifically this bond right here between the second and the third phosphate, this bond ends up being broken oftentimes to release energy in a cell. Okay, and so that's ATP. On the next slide, we're going to kind of show how that energy release works here. So here we have a quick view of that hydrolysis of ATP. And we're starting with an ATP molecule up here on the top, ATP molecule, which again would have energy stored in that bond right there. And if we do hydrolysis, so adding water, breaking that bond, we end up with that one phosphate being left by itself over here, and then this is now called a DP, D for diphosphate. Anyway, and it releases energy, so this is the payoff over here, energy. Specifically, how much energy per mole of ATP? It's going to be 7.3 kilojoules, or kilocalories, excuse me, kilocalories is the unit they're using, per mole of energy. What that can be used for is we can take the energy that's released there, and that's enough energy to feed into a reaction that requires 7.3 kilocalories per mole or less. Okay, so if it needs more than that, then we'd have to use 2 ATP or something like that. But we have enough energy to run a reaction that would require less than 7.3 kilocalories. So let's take a look at an example of that. The example that we're going to use here is the production of an amino acid called glutamine. Get my pen going here. Glutamine, and glutamine is very useful in the building of proteins and a bunch of other things inside of our cells. But it is produced by taking glutamic acid, which is something that you would actually find in a cell, consume in a cell in nature. We'd find that, and then ammonia. okay, which is something you can also find in cells. But glutamine is what is actually required to do the building of these proteins. So anyway, this is something, if we're putting two molecules together, it's going to be an endergonic reaction. We see a positive delta G here. So this is not a favorable reaction, but the cell needs it to happen. So the way we can do this is we can hydrolyze ATP here. So we have ATP. The reason it's in this like yellow star thing is because they think of ATP as a high energy molecule, just because it provides energy for a lot of things. And we're going to hydrolyze it, which is going to release energy. Okay, the energy released is 7.3 kilocalories per mole. The energy required is 3.4, so we have more than enough energy. We actually have some leftover energy, and our total, if we took the 7.3 that's released from the one reaction and the 3.4 that's required from the other, we have an overall, the two reactions together become a negative 3.9, and if I can do the two of these together, my delta G being negative 3.9 becomes favorable, and so a cell can force a reaction that typically wouldn't happen here. We can force it to happen. We can actually make it favorable if we can couple it to this other reaction, the ATP hydrolysis. Okay, so that is the idea of coupling the two reactions, the ATP coupling. Now let's look at some mechanisms here, like how exactly does ATP do this? This energy, this is kind of a misidea. Oftentimes we'll draw like a little arrow showing the energy flowing from the one reaction to the other, and that's not how it really happens. It's not like energy shoots through the air or through a cell's cytoplasm and causes something to happen, another reaction to happen. So next slide here, we're going to look at a diagram that shows the mechanism that allows us to transfer the energy from the one reaction to the other. All right, here's the examples of how ATP is used to drive these endergonic reactions. And basically what it does is something called phosphorylation. And phosphorylation is, see, we got the word right up here, phosphorylation is just adding a phosphate to some molecule, some organic molecule. And so what ends up happening most of the time with this coupling of the reactions is ATP will be hydrolyzed, releasing that phosphate, and an enzyme will take that phosphate and stick it onto something. Okay, and when it gets stuck onto something, it can cause a reaction to happen. Now, they're showing a couple of these. They're showing like a motor protein here that's moving, so the phosphate, and I'm not going to talk about the top two examples here. I'm going to talk about the bottom one because that was what we used on the previous slide. But what happens here is the reason on the previous slide, when it was glutamic acid here, glutamic acid and ammonia, the reason that was not a favorable reaction is because ammonia is relatively stable and glutamic acid is relatively stable. The reason they're relatively stable is they have low G values, or they have a low amount of energy. And remember, the more energy that's stored in a molecule, the less stable it is. The less energy that's there, the more stable. So we have these two molecules that are relatively stable. And so what will happen when we take ATP and hydrolyze it and release that phosphate, if we can take that phosphate, and an enzyme does this, take the phosphate and stick it onto to the glutamic acid, it'll take that relatively stable glutamic acid, and we're actually going to be adding energy to it, adding free energy to it, G, all right, and making it less stable. There's a little bond right there that I'm pointing to. That bond is energy, and so now this phosphorylated glutamic acid is not very stable. Okay, and because it's not very stable, it's more likely to react. Okay, and so this reaction now becomes favorable. All right, because we added that phosphate to it, and then it will be more favorable for this to happen. And that is that's how ATP often works. Take the phosphate from the ATP, put it onto another molecule, and it's going to make that molecule less stable, and then we can get the reaction to happen that we want. It's actually, if you really wrap your mind around it and kind of think about how it's actually happening in a cell, it's genius. Like, it's amazing. This little process of adding phosphates is a very simple way of getting a lot of work done. And every time I say genius, I'm very much pointing towards a creation on that, or a creator, because it's such a simple mechanism that can be used for so much. But that's that. Slip to the final slide here. Okay, last idea here is the idea of, I'm going to call it the ATP cycle. I think the book actually calls it the ATP cycle also, but the ATP cycle, and the idea here is if I take ATP and I hydrolyze it and turn it into ADP and use the energy released to do an endergonic reaction, that's great. But when all said and done, I still have ADP and a phosphate. And cell is incredible at recycling materials, and so the ADP in this phosphate can be taken back to another area where exergonic reactions are being done, and take the energy from those exergonic reactions to stick that phosphate back onto the ADP and produce ATP. And then it can go and drop off energy for an endergonic reaction and go back to an exergonic reaction and pick up energy. And so we have this cycle going on so that ATP and ADP are constantly being converted into each other. And it is the ATP cycle, which we will actually in some future chapters talk quite a bit about the mechanism for all of that happening. But there is your section 8.3, all about ATP and how it's used in the body. Hope you enjoyed. Have a great day.